So now we will move on to a new finite state machine, what we call non-deterministic finite automata. So first of all, we have to understand that what is a non-deterministic finite automata. In case of deterministic automata, what we have seen, let's take an example over here. Uh, we have seen that if you are in some Qi state, on seeing a particular symbol W, you can reach to say Q1. So it is already defined that for a particular symbol, what is the exact destination where you can reach from a particular state. But in case of non-deterministic finite automata, you can have actually multiple option to change your state. Something like, I mean, if I take the same example, if you are in Qi and on seeing W, you can not only reach Q1, you have an option to reach Q2 also, option to reach Q3 also, option to reach Qn, any number of states. I mean the valid states that is present in the finite state machine for the same input W. So now naturally question will come that why we will think about doing this. Always remember one thing, that non-deterministic machine doesn't really exist in practical life. So why we go for non-determinism and why you go for non-deterministic machine designing? The reason is that in some cases, in some situation, it has been seen that designing, I mean finding a solution of a problem is easier if we think in a exhaustive search way. If we have an exhaustive search means you start from a point and you check all the possible options, all the possible path to reach to your goal. So if you want to do an exhaustive search, that means you cannot restrict yourself to go to a particular path for a particular input, because you have to check the other options also, other path also for the same input. And from this point, the non-deterministic finite automata came into the scenario. So NFA, I mean in short it is NFA. So NFA say that you can reach to any number of states from a particular state in the finite state machine. Now generally the problem of backtracking is highly applicable in this particular situation. Backtracking means you are trying to solve a problem, you are taking a particular path, and certainly if you realize that your path is wrong, you go back to your initial state and then you start to a new approach. That is what we call backtracking, which we frequently use in our daily life to solve many practical problems. But as I told you, that practically in a real life non-deterministic machine doesn't exist, then how we can relate the non-deterministic solution In a practical life, obviously this question will arise. To solve this situation, this issue, we have an option to convert the non-deterministic machine to a deterministic machine also. Each and every non-deterministic finite automata can be converted to corresponding deterministic finite automata. So we will see how we can define this. We can actually design the non-deterministic finite. How we can convert a NFA to a DFA. We will see it later. But before that, let's take some example of non-deterministic finite automata. So for example, we have a language something like W belongs to a very simple situation I am considering. AB star where W starts with B. So obviously B, A, B, any string after B will be accepted. We can design a non-deterministic machine something like in this way. Like you can take a initial state and we will think about only the correct strings. So I will see about this B. This is 1 and then we have A or B. So this is a possible NFA, although I don't have multiple option to reach to solve a particular problem. Okay, so we can take another problem, something like suppose I start from Q0, I take two paths. In one side I take A Q1, okay, and then again A Q2, and suppose I'm writing say okay, so suppose this is a one site that I want to, what particular string will be accepted? Only A will be accepted, otherwise anything will be rejected. But I want to accept A also, 3A. So in that case I can take another option Q3, Q4, Q5, and this is also the final state, and it is possible I can have more than one final states in the DFA. So that means you see, suppose we have A, okay, AB, anything. No, not AB, suppose only B. Okay, and here also I have a B. So what I can say, this particular NFA can accept a language either A, B to the power n, or it can accept b to the power n. Either of these two, either this one and this one, both will be accepted. So when you start journey from here, you are about to start reading the characters, you don't know how many a is there. If you find, that means we have to take a non-exhaustive search, that for this type of string, which path I have to follow I don't know. For this particular type of string, which path I have to follow I don't know. That's why I can take an exhaustive search, and one of them will be used to accept a particular string of type either a b to the power n or a b to the power n, where n is obviously greater than or equal to 0. Because I don't know, maybe b will not even repeat it once. That's why I have written n greater than or equal to 0. So this is one more example of non-deterministic finite automata. Now question is that what will happen? I mean, for example, if I take this particular example, what will happen in this particular case if the string starts with an a? For example, a b b. Obviously this string will be rejected. But one more difference with respect to DFA is here, that is, in case of DFA, there is a transition for each and every symbol from a particular state. What I mean that if we want to design the DFA, we have to think about each and every symbol from each and every state. But in case of NFA, we don't need to care about that. That means if you are in Q0 and if you find A, since Q0 on A is not defined in this particular design, so naturally the machine will stop. But in case of DFA, it is explicitly defined that what to do. And generally what we do, we keep a trap state that already we have seen in previous classes. We keep a trap state, and in the trap state we put that particular machine and it will never come out from the trap state. So this is a very important difference. So let's repeat, I'm repeating it again, that in case of DFA, there is a transition for each and every symbol from one state. But in case of NFA, the transition for some symbol may not be defined for all the states that we consider. In that case, we write Qi, say for example Q0 on A will be considered as phi, a null state. So now let's move on with the other part of the NFA. So a very important thing is that epsilon move. This one, epsilon move. So question is that what is epsilon move? This epsilon we have found as a null string, I mean empty string, not null string, as an empty string in a language. So NFA has a power, we can actually say it's a epsilon NFA. So NFA has a power, we can give a power to the NFA that it can read, it can actually change its state without consuming any symbol. What does it mean? It means, if I take a very simple example of a DFA or maybe NFA, whatever you can say I have Q0, on 1 I'm going to Q1, on 0 I'm going to Q2, say, which is final state, okay, and on 0 say I am in Q0, and on here on 1 I am in the Q1, something like this. Now see, if the input is something like 1 1 0, when you are about to start reading this particular string, you are in Q0 state, because Q0 is the initial state. On consuming this particular symbol 1, since you are in Q0 state, that's why you will reach to Q1 state. Now to change the state from Q1 to some another state, or maybe the same state, you have to read a particular symbol. For each and every symbol reading, we actually change to a new state or remain in the same state. But without reading a particular symbol, you cannot move on. The machine cannot move on. Which restriction was not present in case of epsilon NFA. Since epsilon is basically considered as an empty string, and string can be of only one symbol also, that means you can say that this particular 110 can be written as 1 and 1. In between the two 1 we have an epsilon. In between this 1 and 0 we have an epsilon. Not only one epsilon, you can have multiple epsilons. Then a 1. Since this is an empty string, this is basically what we call empty string. That means in the original string, this particular epsilon will not get reflected. That means if we have a situation something like this, epsilon, 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 then a 0. Since these epsilons are basically empty strings, so as a whole this will get represented as 110, because this epsilon is not visible, it is an empty string. But you can keep in this way within a particular string. Now NFA has a capability to consuming these epsilon symbols. So considering a particular string is same as considering any number of epsilon within the characters of the string, right? So if we consider that this is a NFA, it can be NFA also, right? It can be NFA also. I mean, if I just forget about this 0 part, I mean, let's omit this 0 part and this 1 part, it's an NFA, right? You can consider. Now if I want to actually consuming this epsilon in the NFA, we can redraw the diagram something like Q0. On epsilon it will go to Q1. On 1 I will go to Q2. Then on epsilon I will go to Q3. And then on 0 I will go to Q4. So what this epsilon means? I mean, if you start journey from Q0, since epsilon is given, it means that without consuming any symbol in the string, I mean, suppose the string is given 1 0, I mean say 1, and here it is given another, suppose that as self-proof is 1, so 1 1 1 0, suppose the string is 1 1 1 0 is given. So how you can start? Since epsilon is given over here, it means that you can assume that a epsilon present is before 1. You can assume it easily. because epsilon is invisible, which is an empty string. So in the original formation, the epsilon will be vanished. But you can imagine it at the time of accepting a particular string through a machine. So if you have this symbol, you are in Q0 state. On consuming this epsilon, you will reach to Q1 state. In other words, you can say that without consuming anything, because ultimately in the with respect to the practical scenario, this epsilon doesn't have any existence. That means I can say that without consuming any symbol, you can change your state from Q0 to Q1. And that is a powerful part of the epsilon NFA. So if we just see the definition of a NFA, or maybe epsilon NFA, whatever you can say, in the definition of DFA and NFA is almost same, only difference will happen in case of this delta transition function. Because in case of delta transition function for a DFA, what we have seen? We have seen, for example, over here, suppose here, that we have say n number of states and m number of transition, m number of symbols, and depends on n number of states and n number of symbols, you will ultimately go to one of the n number of states. So in case of DFA, the delta function is a mapping between Q combination of this sigma, which will map to Q itself, right? Because Q is the number of state. I mean, actually the number, not the number of state. Q is the state of the states. On some, if you are in some state and on seeing a particular symbol which is present in this sigma, you will reach to one of these states that is in Q, right? But since in case of DFA, in case of NFA, we have seen that we have multiple choice to reach to one of the any states. That means you can say that from Qi, you can reach, if I consider that we have a set of the states from where you are, where you belong right now, and this is the set where you will reach. From Qi, you can reach to phi state. Why phi I have written? Because if the symbol is not specified, we say we will reach to phi step. That I have just showed you over here. Since A is not written, what to do if you are in Q0 and if you get a symbol A, and what to do, it is not defined in this NFA, then we say that we will reach to state which is phi, an empty state. So that means I can say that I can reach to phi, I can reach to Q1, I can reach to Q2, or maybe I can reach to combination of Q1 and Q2, both there is a possibility. So that means if I consider that I have only two states, Q1 and Q2, I mean Q1 and Q2, so for example Q1 is a state and Q2 is another state. Say just for B I have written this Q2. Okay. Even say for example Yes, I can reach to remain here, something like this. So on Q1, from Q1, you can reach to 5, because if you get A, you will reach to 5. If you get B, you can reach to Q1, or you can reach to Q2, or you can reach to both Q1 and Q2 for the same B. So that means the number of possible options that you have is basically, you can say, 2 to the power q, where q is the number of states. So that means, and here is the difference actually with respect to the DFA. In case of DFA, we had a situation just shown you that q with sigma to q, but here it will be q with sigma, I'm sorry, q with sigma, you can reach to any superset of the combination of the states, that is 2 to the power q. But now if you involve the epsilon here, this sigma will be basically, you know, we will basically take a intersection, not intersection, sorry, what is the name of this particular operation? Just anyway, I mean, it's not coming in my mind right now. So just sigma, it has to be added, I mean, sorry, the epsilon has to be added with the sigma, right? Okay. So there is a possibility to, you can involve this epsilon with the sigma, but ultimately there is a possibility to reach one of these 2 to the power q states in case of a NFA, but the other part will remain same. Okay. So now question is that let's take some example of the NFA that we have over here, epsilon NFA especially. You see something like this, and what does particular this mean? This particular diagram shows that you can change your state from q0 to q1 without consuming any symbol, but when you will come back to q1 to q0, you have to consume at least a 1. And if you draw the corresponding transition table, you see it is given that it's not only given 0 and 1, it's given a epsilon also. That on q0, if you get 0, you will remain in q0. If you get 1, you will remain in an empty state. But if you get epsilon, I mean, if you just imagine that you have a epsilon, you can reach to q1, and epsilon doesn't really exist in practical life, so that means I can say that without consuming anything, you can reach to state q0 to q1. So these are actually giving more non-determinism in the problem solving technique. As more exhaustive search you want in your solution, your NFA will need more power. And how you can increase the power? This is the way of increasing the power of NFA, considering an imaginary epsilon uh, symbol in the alphabet. So this is basically actually what we have seen till now about the NFA. Just I have discussed about this, that non-determinism is equal to backtracking. Basically, you can also think a very practical situation that you are giving an exam of an MCQ, you have some question and the question has multiple answers, A1, A2, A3, A4. So what basically you do, you start solving this problem and somehow you try to reach this particular state, and if you find that somehow it is not possible to reach to this answer, you go back and you start from this Q1 to find this Q2 again. If it's not possible, then again you go back and maybe you are trying to find out some answer, some path to find this answer A3. And this particular situation is called backtracking. And this is what happened in real life. You have faced this situation many times, maybe in your exam. If you know the answer correctly, if you have a deterministic solution to solve the problem and find the one of this answer among A2, A1, A2, A3, A4, you will just start from Q1 and will basically take the correct path among these four cases and reach to the solution, right? But if you don't have any idea, then basically you follow arbitrarily all the paths and find which is basically the best one. So that means among all the non-deterministic exhaustive search, one of the solution is deterministic. So that means if you think about the set of solution you can find through a non-determinism and the solution that you can find through determinism process, you will realize it that determinism basically actually a subset of non-determinism, because through non-determinism you can go through the same problem, you can find the you can find the same solution. In case of determinism also you can find the same solution, but in case of determinism you will not think about the other solutions, which is other paths which are not going for correct solution. So naturally question will come that are they same? Are they same? That mean obviously some people may imagine that mean the NFA is more powerful than DFA. Is it true? Unfortunately, this is not true. From all this different study, you cannot say that NFA is more powerful than DFA. The reason is that although the solution we are thinking in non-deterministically, since actual machine is not a non-deterministic, real machine is not possible to a non-deterministic, that means each and every non-deterministic solution has some deterministic solution behind that. That means with respect to the powerfulness, NFA and DFA is basically same. NFA is, sometimes we prefer NFA just to do the exhaustive search on the solution, but with respect to the actual solution we have only one path. Among all the exhaustive searches, ultimately we have to find out only one path, which we can find out directly through the DFA. That is the difference. So we will see how we can convert the deterministic finite, I mean sorry, a non-deterministic finite automata to a deterministic finite automata in the next class.